Today's lesson is over section 5.1, Areas and Distances. First, we'll start with a warm-up problem. For these following figures, please find the area. Take a moment to pause the video, find them, and then restart when you're ready to see the answers. As you can see from our warm-up problem there, we're going to be talking about finding the area of some figure or some place or space. Now, for our problems and purposes, we're not going to be always given a geometric shape to find the area of. It's going to be us finding the area underneath a curve. And so, under a curve, you're going to be given a function with a starting x value and an ending x value. And we're going to be looking for the area of the space between the curve and the x-axis. So we're not going to be looking at below the x-axis because obviously that goes on infinitely, but we're going to restrict ourselves to that area. So here for this example, I want to find the area or estimate the area of the curve underneath of x squared plus 1 between 0 and 2. Okay, now there's lots of different ways of doing this, and we can break this down using geometric shapes that we already know. So I have these graphed, and we can kind of do this three different ways. We can use the left endpoints, right endpoints, and midpoints. Now what I mean by those is a left endpoint is, notice how I drew those rectangles, the point in which they touch the curve. It's on the left side of the rectangle, okay? And so right endpoints would be on the right side of the rectangle, and midpoints would be in the middle. So left endpoint for this one, now notice I'm trying to, like for rectangles, I want to be able to use just the normal formula of base times height. And so breaking this down, the width or the base of each of these rectangles is going to be 0.5 because I have 4 rectangles or 4 sections, and because I'm in between an area between 0 and 2, that breaks down into 0.5 of a width. And then each of those endpoints are a x value, and so I know what the height will be because it's the y value attached to those x values. And so when I plug those in, I'm able to find that based on the left endpoints, my area would be 3.75. I can do the exact same thing with my right endpoints. Now it's going to be the same width because it's the same number of sections. So 1/2 or 0.5 is that. Now notice that you use some of the similar x values, except instead of 0 we'll have 2 because 0 doesn't touch on the right side of one of our rectangles. So plugging in those values, you're able to find that the area of this figure would be 5.75. Now notice that one is smaller than the other. This kind of creates an upper and lower bound kind of situation. Now midpoints would be in the middle. So using the same width, it's where that width would be in the middle or hit the middle of your rectangle. So it's like in between the left endpoints and the right endpoints a little bit. So this one should be this area should kind of fall in between the two values or areas that we already found with estimation. And so that means that halfway in between would be an x value of 0.25, 0.75, 1.25, and 1.75. Now notice it's the x value that we're midpoint in, not the y value. Okay? And so when I plug all those values in, here the midpoints will usually give us a little bit more of wonky values. Notice all the decimals that I have here. But the midpoint usually will give us a better estimate of what we're looking for. And so here I get 4.625, which falls in between 3.75 and 5.75. And so that kind of should be our best estimate. Now sometimes you're not given information that allows you to find the midpoint of all those, so the lower and the upper bounds will be what you need to have. So Example 1, we're doing the same thing, except I'm looking at the curve of 1 over x using 4 rectangles, so the same number of sections, but now I'm going to be restricted in between 1 and 2. So I graphed it real quick. So looking at the left side here, I'm going to break these into 4 rectangles. Now here, those x values will be 1.25, 1.5, 1.75 in between there, okay? And so each width of this will be 1/4 because 2 minus 1 would be a distance of 1 divided into 4 sections would be 1/4 for each section. Okay, and I'm doing the same way. Now notice that I have a function to plug this into. Sometimes you're just going to be given a graph, and so the y values that you're going to be using, you're going to have to just make guesses based on what the graph gives you. So just know that you're not always going to have a function. You're just going to have to make some good guesses. But remember, it's an estimate. It's going to be sometimes not fully right on. Okay, so the left endpoints gives me a value of 0.7595. And then the right side here, knowing that I got some similar values here, allows me to get the value of 0.6345. So then the midpoint should kind of fall in between here. So here for the midpoint, I'll use 1.125, 1.375, 1.625, and then 1.875. And that allows me to get 0.6912. Okay, so that's probably the best guess right there, best estimate. For example 2, we would like to suppose the odometer on our car is broken and we want to estimate the distance driven over a 30-second time interval. We take speedometer readings every 5 seconds, and we want to record them on the following table. Now here, notice that time is in seconds, velocity is in miles per hour, so we need to convert these values into the same thing. So what I did was I took each mile per hour and multiply it by 5,280 divided by 3,600 to convert it to feet per second. And I got the following values there. And then from there, now it's very similar to what we've done in past. So we're breaking it up into 5-second increments. So it's like each rectangle is 5 seconds. So that's our change of x. And for the first one, we're looking at the left side. So if I'm looking at 0 to 5, 0 is the left side. If I'm looking at 5 to 10, 5 is the left side. So that's how I get those values for the left side. Right side is the opposite. So 0 to 5, 5 would be the right endpoint. And then 5 to 10, 10 would be the right endpoint. And so plugging those values in, using my feet per second, I'm able to figure out how far I've traveled in feet. So it looks like the car has traveled between 1,129.3 repeating feet to 1,209.9 repeating feet. For example 3, now we're going to be given some functions that might make it a little easier for us to give not just an estimate, but actually find the actual area under the curve, is because these shapes are a little bit more geometric. So letter A here, this one's actually a fourth of a circle. So if I had rewritten this function into changing the f of x to y, you get y squared plus x squared equals 1, which is an equation for a circle. So using the circle formula, I'm able to find that pi r squared, so the radius is 1, gets me pi times r, or 1 squared, but then a fourth of that gets me pi to the fourth. Letter B, drawing that line and then making the lines connect to the x-axis gives me some triangles. And so because x-axis is like where we're going above and below, the triangle that's below is actually a negative triangle for area. So I find the area normally, but then when I want to actually find it, it's a -4 rather than a +4. So that gets me -3. And then C is very similar. I have 3 different functions going on at the same time, so it's like a piecewise. So it looks like I have 4 triangles, 2 below the x-axis, which are negative, 2 above, and then I've got a little square there for an area of 1. And so once I find all the areas, and here they are all simple calculations, so that's why I'm not like showing all those values. And so I kind of add them all up. So the negative one's going to go together, so that negative 1/2, 1 3/2, and then the top 1/2 and the top 3/2 go together. So it gets me -3 plus 2, which is an area of -1. Okay, have fun.